In this video, we will be discussing the development of the modern periodic table by Dmitry Mendeleev, as well as indicating some of the different regions on the periodic table. In 1869, the Russian chemist Dmitry Mendeleev published his version of the periodic table. While there had been previous attempts to categorize the known elements into some sort of a tabular form, Mendeleev's periodic table was the one that we use today. In developing the periodic table, Mendeleev put the elements in order according to their atomic masses. So you would have hydrogen being number 1, then helium, lithium, beryllium, boron, and so forth. What he noticed was that there were repeating patterns of the behavior of the elements. So for example, in certain cases, hydrogen bonded in a similar fashion to fluorine, which binds in a similar fashion to chlorine. Then we have helium, neon, and argon, which all tend not to form chemical bonds. What he noticed is that the repeating pattern reoccurred every 8 elements. By taking into account the repeating patterns that he noticed in the reactivity of the elements, Mendeleev's periodic table was organized so that the known elements at the time were put into a table-like format. He arranged the rows so that the elements that had similar properties would fall in the same vertical columns. What made Mendeleev's periodic table unique was that he used it to predict things. Several of his columns contained gaps, which allowed him to predict the existence and even some of the properties of yet undiscovered elements. Mendeleev predicted the existence of an element called Eka silicon, which we now call germanium. He also predicted Eka aluminum. So the germanium, which he called Eka silicon, was found directly below silicon. And what he did was he predicted that because it was in the same column, that this germanium, also known as Eka silicon, should have similar properties. So he predicted that the atomic mass, his prediction for the atomic mass was that it should be about 72 atomic mass units. When germanium was discovered, it was found to have an atomic mass of 72.64. Mendeleev predicted that the density, based on silicon and other things within that silicon column, that the soon-to-be discovered germanium should have a density of 5.5 grams per cubic centimeter. It was determined to be 5.35. He predicted that when it was forming an oxide, that it should form one of the elements of Eka silicon or germanium to 2 oxygens, and it was discovered that this was the case. Similarly, when reacting with chlorine, it should form a chloride with 4 chlorines per germanium or Eka silicon, and that's what it did. He also made predictions for gallium, which falls directly below aluminum. He predicted that the atomic mass for the soon-to-be discovered gallium would be somewhere around 68 atomic mass units. It was found to be 69.72. He predicted that it would have a low melting point, and it has a melting point of 29.8 degrees Celsius, which in terms of metals is very low. He predicted a density of 5.9 grams per cubic centimeter, which is exactly what it is. He also predicted the different reactivities that it would have, similar to what he did for germanium, and these turned out to be correct. So because Mendeleev left gaps in his periodic table and used his concept of the periodicity, the repeating pattern nature of his periodic table, to predict unknown elements that were later discovered and that had the properties that he predicted, it gave a lot of credence for the use of his periodic table. The modern periodic table has a very similar format to the one that Mendeleev initially proposed. In the modern periodic table, the elements are listed in order of their increasing atomic number rather than the increasing relative mass. For the majority of the elements, the order is the same, but because of isotopes, which was not known at the time of Mendeleev, there are a couple of elements that would be put in a different order. So for example, something with a lower atomic number actually has a higher relative mass. Some nomenclature that goes along with the modern periodic table is the rows. Instead of being called rows, they're referred to as periods. So you would have the first period, which has hydrogen and helium, the second period, which starts out with lithium and ends with neon, the third period, which starts with sodium and ends with argon. So these are the different periods. The rows are called periods. Columns are called groups. So you have group 1, group 2, and then there are a couple different ways of naming the groups that boron, carbon, nitrogen, oxygen, and so forth belong to that we'll get to in just a second. The elements in a group or family have similar properties. Note that Mendelev's periodic law predicts the pattern but does not explain why the pattern or similarities in properties occur. This goes back to our discussion of laws and theories. Mendelev's periodic law is a summary of a large number of experimental observations, but it does not explain why the pattern occurs. It actually falls upon quantum theory to explain the why. So modern quantum theory is able to explain why the periodic table looks the way that it does and why different elements have patterns that repeat in a periodic fashion. There are several different ways of dividing up the periodic table. We can look at the behavior of the elements in their elemental form, and in doing so, compare their reactivities. When we do that, we can categorize the elements into three subcategories: metals, nonmetals, and metalloids. Metals are in the bottom left of the periodic table and would have what we traditionally consider metallic behavior. They tend to be shiny in their elemental form, they tend to conduct electricity, and they tend to be malleable, which means that if you hit them, they tend to deform. Nonmetals are found in the upper right corner. They tend to not conduct electricity, and in their solid forms tend to be very brittle when struck. The region between the metals and the nonmetals is called the metalloids. You can pick it out on the periodic table by, typically you'll see a dark staircase pattern written on periodic tables. The ones that touch the staircase are the metalloids. They have characteristics that are halfway between metallic or metals and the nonmetals. So they tend to conduct electricity somewhat well, and these are what we use to make semiconductors. And when they form solids, they tend to be somewhat malleable but somewhat brittle. We can also categorize the elements based on their overall reactivity, in which we call some of them main groups and other ones transition elements. The transition elements tend to form much different types of compounds than the main group elements. So the main group are the first and second group, as well as group 13, 14, 15, 16, and 17, and 18. So when you're looking at the periodic table, they are the two larger or taller portions of the periodic table. The transition elements are the ones that are sunken in a bit and are located down here. In terms of numbering of the groups of the periodic table, there is the group number. There are two different ways of writing out the group number. There is the historical method that involves labeling them based on whether they are a main group or a transition element. So you would call the first group 1A, then 2A, and then your next set of main group elements would be 3A, 4A, 5A, 6A, 7A, 8A, and the transition elements start out as 3B, 4B, 5B, 6B, 7B. Then it gets a little bit obscure in this region here. A better method, and the one that is now used, is just calling them based on which column they are in the periodic table. So you have group 1, group 2, 3, 4, 5, 6, 7, 8, all the way up till group 18. So again, the current method is the one that uses group 1 through 18 and does not use the A's and the B's. But you should be familiar with the fact that there are two different representations depending on if you're looking at fairly old literature, which might have the A and the B when denoting the different groups, or more modern literature, which has the 1, 2, 3 up to 18. While many of the groups of the periodic table have their own distinct name, there are 4 that we will be referring to again and again as this semester continues. They are the alkali metals, which is group 1, the alkaline earth metals, which is group 2, the halides, which is group 17, and then the noble gases, which is group 18.